Okay, let's dive right into this explainer and demystify exactly how modern computers actually learn to see. We're going to explore the absolutely incredible vision transformer model based on the fascinating work of Dr. Abdullah Al-Amarin. If you've ever wondered how artificial intelligence processes the visual world around us, well, you're in exactly the right place.
It's a really great question to start with. How does an algorithm that was originally designed to read text, like the model's power in today's chatbots, how does it manage to understand and classify a photograph of a cat? Text is naturally sequential, right? We read one word after another. But an image? That's just a massive, simultaneous grid of pixels. So how do we bridge that gap? The answer is the Vision Transformer, or VIT. Instead of trying to just swallow the whole image at once, this architecture brilliantly turns a photograph into a structured, step-by-step puzzle. It splits the image into manageable patches, and then uses this powerful process called a self-attention mechanism to figure out how all those puzzle pieces relate to one another. Here's our roadmap for today's explainer. 1. Meet the Vision Transformer. 2. Breaking images into patches. 3. Queries, keys, and values. 4. Calculating attention scores. And 5. The final classification.
Okay, section 1, meet the vision transformer, the big picture. Now, what's really interesting about the overall architecture is the overarching flow. While the whole diagram might look a little complex at first glance, I promise you, by the end of this explainer, you're going to understand exactly how an image moves from the very beginning up through the linear projection and transformer encoder, all the way to the final classification at the end. This is literally the entire roadmap of how a machine sees.
Moving right along to section 2, breaking images into patches, creating the puzzle pieces.
Rather than looking at every single static pixel at once, which honestly would completely overwhelm the system, the Vision Transformer splits the image into distinct patches. The algorithm typically cuts the image into 16 by 16 pixel squares. It's literally like taking a pair of scissors to a physical photograph and snipping it into a grid.
To make this super clear, for our example setup today, we're going to follow 4 specific, isolated patches from a picture of a cat. We have patch 1, the cat's head, patch 2, the cat's body, patch 3, a blank piece of the wall behind it, and patch 4, a textured piece of the rug it's sitting on. But here's the catch, right? Once we cut up the image, we completely lose the context of where those pieces go. If you scramble a puzzle, you don't know what the picture is anymore. To fix this, after flattening and embedding these patches into raw data, the system attaches a mathematical name tag, which Dr. Al-Amarin's source refers to as positional encoding. This ensures the model perfectly remembers where each isolated piece originally belonged in the layout. No lost pieces here.
All right, section 3, queries, keys, and values, the language of patches. Now that our puzzle pieces are ready and mathematically tagged, we enter the most critical part of the source material, the self-attention mechanism. This is genuinely where the magic happens. Each of our 4 embedded patches, the head, the body, the wall, and the rug, is passed into separate, learnable linear layers. The architecture transforms every single patch into 3 distinct mathematical vectors, Q, K, and V. But what do those letters actually mean for our cat?
Think of it, actually scratch that. It's exactly like a matching game at a networking event. The Q, or query, is a patch asking a specific question. The K, or key, is what the other patches are offering as a potential match to that question. And the V, the value, well, that's the actual valuable content or features that'll be shared if a match is successfully found. Which brings us to section 4, calculating attention scores, connecting the dots. Let's dive a little deeper into the math to see exactly how these queries, keys, and values interact to actually help the computer understand it's looking at a cat. Calculating this attention happens in 3 very logical, sequential steps. Together, these steps generate a score that dictates exactly how much focus or attention one patch should give to another. First up, we compute the dot product between a query and a key. Let's take patch 1, the cat's head. We compare the head's query against its own key to find its self-similarity, so Q1 times K1. Then we compare the head's query against patch 2, the body's key, Q1 times K2. This mathematically tells the algorithm how strongly the head relates to the body, and it does this for absolutely every single patch combination. Once we have all those raw scores comparing the patches to one another, we move to step 2. We apply the softmax function.
Now, that sounds fancy, but it's just a mathematical function that takes all those messy raw attention scores and elegantly normalizes them across all the patches. It converts them into clean, proportional weights so the system knows exactly which patches are most important to the cat's head, scaling them perfectly.
Finally, step 3, we compute the brand new representation for the cat's head. We do this by taking those normalized attention weights, which we'll call S, and multiplying them by every single patch's value vector, V. And then we just add all of them up. So the new output for patch 1 is a weighted sum of the values of the head, the body, the wall, and the rug, based strictly on how much attention it decided to pay to each one. And this brilliantly illustrates why we multiply by V in the first place. As Dr. Alamaran's notes emphasize, the value vector holds the actual image features. The Q and the K, they just tell the system where to look. But once the attention mechanism decides which patches are relevant, multiplying by V allows the model to actually gather and summarize that relevant content.
On to section 5, the final classification, making the decision.
So, we've successfully processed the patches, mapped them, and calculated their rich relationships. But how does the vision transformer take all of that and make its final decision? Well, enter the manager of the entire operation, the Special Classification Token, or the CLS token. This is an extra learnable piece of data added right at the beginning of the patch sequence. It has its very own query, key, and value, and its sole job is to attend to all the other patches to aggregate a complete global understanding of the entire image. This global aggregation happens through a series of final steps inside the transformer encoder block. As the data passes through multi-head attention layers and feed-forward networks, it undergoes an intense refining and normalization process to ensure the final output is perfectly structured. And finally, we reach the end of the journey. The CLS token's comprehensive, globally aggregated output is fed directly into the MLP head. Because it has successfully paid attention to the relationships between the furry head, the paws, the rug, and the wall, it can confidently output the final prediction. Yes, this is definitely a cat.
So, what's the absolutely crucial takeaway you should have from this explainer? It's that vision transformers succeed by fundamentally changing how computers see. They don't treat images as static, isolated pixels anymore. Instead, they treat them as a rich, interconnected web of relationships, learning context, just like we do when we look at the world around us.
Which leaves us with a pretty fascinating final thought to ponder. If an algorithm can achieve such a high level of understanding of a photograph purely by mapping the mathematical relationships between its fragmented pieces, what complex mysteries and entirely new fields of data could these self-attention algorithms unravel for us next? Thank you so much for exploring this with me today.